Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our Finite Element Analysis and Design software, RFEM. The title for today's webinar is Form Finding and Cutting Patterns of Membrane Structures in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer. We are located in Philadelphia, Pennsylvania. My colleague Lucas Sunel will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Tiefenbach, Germany office. If the control panel does seem to get in your way when you logged into this GoToMeeting, feel free to show or hide it with that orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I'll certainly send you a follow-up email afterwards. So as far as the content for today's webinar, I want to give you a brief overview of RFEM and in particular the add-on modules RF form finding and RF cutting patterns for tensile type structures. Then we'll move on to a specific example in RFEM, including modeling, form finding, and the design of a membrane structure. We'll touch on the overview of the supporting structural design, including AISC design code checks. And lastly, we will generate the cutting patterns of the membrane elements and export these to AutoCAD. So RF form finding is a module extension within our main program RFEM. This allows us to perform the form finding procedure of membrane and cable structures. The form finding process is performed iteratively according to URS, which is the updated reference strategy by Professor Bletzlinger and Professor Rahm. Now this is a very complex process, but it also is one of the most accurate processes. We can also take into account both isotropic and orthotropic membranes, which we'll see in today's example. We can consider self-weight, free loads, and internal pressure during the form finding process. And lastly, we can take into account the interaction with the supporting structure. Again, I'll show you that with the example today. Our other add-on module, RF cutting patterns. Well, this uses the minimum energy method for a very accurate cutting pattern. So essentially, we're turning this 3D member element into a 2D cutting pattern via the minimum energy method. We can also take into account uniform or linear compensation by warp or weft directions, meaning typically these membranes are going to be stretched when they're applied to our structure. So for the 2D cutting pattern, we can take into account that compensation. We can also apply these compensations for boundary lines around the 2D cutting pattern, so it doesn't necessarily need to be in the warp and weft directions. We can also allow for different allowances, such as for welding and for boundary lines. Welding for overlapping members, maybe we need some additional material. Boundary lines for the upper and lower portions of the 2D cutting pattern as well. There is adaptable data organization, meaning even after the fact that we have performed the calculation for our 2D cutting pattern, we could go back and easily add in some additional material for welding and for those boundary lines without having to recalculate the 2D cutting pattern. And lastly, I'll show you how to output the cutting patterns both graphically within the RFEM printout report, as well as tables. And these tables can be exported directly to Microsoft Excel for further sorting. And lastly, we can export them as a DXF file, open them up in AutoCAD, and show you how to utilize the cutting patterns this way. So with that said, we can jump immediately into our RFEM model. When we go to open up a new model, we just give it a model name. I called this one RF Form Finding 1. The type of model is a 3D model. And our drop down over here on the right is our load cases and combination generator. So you can see from my drop-down box that I have the ASCE 7 load combinations. I also have our Canadian standard, Eurocode standards, and many other international standards. When I have this checkbox checked, then the program will automatically create those load combinations. You can see that when I uncheck this, then I can manually put in those load combinations if I'd like to as well. It's important under the Options tab when we're utilizing RF form finding and RF cutting patterns to check on these checkboxes. Otherwise, we won't have those options within RFEM. So when you're maybe checking out the form finding of our membrane structure, it's important to check these checkboxes, and then we can launch our model. So up pops RFEM. And you can see here that we have our basic graphical display here in the center. We have our tables to utilize down at the bottom. Over on the left is our project navigator, which again just controls some of the input data. We'll also see our results available here. And lastly, we have all of our tools up at the top. And today we'll be using all of these options. I want to begin with drawing a basic line element. So up in my toolbar, I can choose to draw a new line, and you'll notice that we have many different line types. And you'll hear me say this quite often today, that we have a lot of AutoCAD-like capabilities within the program. So things like complex geometries, which is quite common for membrane type structures, is really no problem to model within RFEM. So hopefully you'll get a glimpse of that today. To begin with, we are just going to do a typical straight line here, and I could draw this graphically in my graphical viewport over here on the right, but I can also just enter in graphically a couple nodes here. So for example, 0, -5, 35, then I go down and click apply, and I can enter in my second node at 0, -30, and 15. And hit apply. So now you can see that we just have this line element in our 3D view over here. I'm going to select this entire line and the nodes and use my rotate copy tool. So here I can specify that I would like 9 copies at 40 degrees, and I'm rotating everything about the origin 0, 0, 0. And even more so, we have a nice feature here down at the bottom. So if I click on this expanded settings, I can create lines between my copy nodes. Even more so, I can create surfaces between those lines. So now when I click OK through all of these dialog boxes, I have my conical structure with just a few clicks of a button. Now turning this into a plan view, and maybe I turn off my grid down here at the bottom, I'd like to create cable elements spanning between my longitudinal lines here. Now a cable element certainly can't be constructed in the field as an arch type line like this. So we need to create straight lines here. Well, how to quickly do this? I'm going to turn this into an elevation view, and I'll highlight all of my members down here at the bottom. Now you'll notice that my table 1.2 lines shows me exactly which lines I have selected in my graphical view. So using this feature within the table, I can show the selected objects only. So these are only my lines selected at the bottom of my structure. The line type right now is set at arc. I'm going to change this to polyline. Then using the F8 key, I can quickly copy that same setting down for all of my line elements here. Now, if I turn this back to my plan view, you'll notice that these are now straight lines, but I still have this node in the middle that I'd like to get rid of. For this, I'll turn this into wireframe view, and now holding down my control key, all I need to do is to graphically select all of my nodes here. Then I simply click the delete key, and I have these straight line elements. So with these line elements, I'm again going to select them graphically down at the bottom, and I'm going to right click to edit the line. Now every cross section within the program is created with a line element underneath it. So we have a nice tab here up at the top called member, and we can create a member availability. Now up pops our new member dialog box, and we can create a new cross section. So here I launch my cross-section database, and you can see that we have many different cross-sections, such as our rolled sections, built up, thin-walled, massive for concrete sections, timber. For these elements, I'm going to utilize the solid sections here. And we have our filters over on the left, which you can see some different producers maybe that are applicable to the Eurocode design. We also have our AISC database. Now I can scroll all the way down to the bottom to choose a 1/2 inch diameter cable element. My default materials within the program are 4,000 psi for concrete and steel A992. I'd actually like to create a new material here, and my material database is brought up. This looks similar to my cross-section database as well. I have my filters over here on the left. So you'll notice that under material category, I'm going to change this to stainless steel. Now I have the ASTM as well as Eurocode down here to select from. Looking at ASTM, I have a very long list of all of my stainless steel materials, probably that I could possibly think of. We can also utilize our favorites list, which I created a favorites list called USA. These are just common materials that I use quite often for projects, and you'll notice I added stainless steel A479 here. Well, I can select this material and click OK through all of these dialog boxes. Now, the member type right now is set at beam. I actually want to change this to a cable member. That's the element that we're trying to model here. So now I can open up the member type. Now this is available because I've activated that RF form finding add-on module. Otherwise you wouldn't see this option available. Here we have the cable parameters for form finding. And with this, we either have geometry or force. With geometry, we can set a target cable length or a target cable absolute sag, relative sag. With force, we can set a force in the cable or a force density. So these are the properties that we'd like to see after the form finding process is complete. When we're choosing geometry, this is maybe relevant for border cables and membrane structures such as what we have today. The force is an option that's maybe relevant for cable webs. For our example, we'll choose a target cable absolute sag of 1.5 feet, and I can click OK. So now that I have set this form finding capabilities, I click OK. And now we have the cable element specified down here at the bottom. So I want to turn this back into the rendered shape to show you guys that right now my surface elements are red. That means that there probably is something missing within the program that is trying to flag me. Well, if I highlight all of my surfaces, I right click and go to edit, you'll notice that my stiffness is set to null. Null means nothing. So we need to put in these material properties as well as our form finding process for our surface elements. So the first thing I'm going to do is use my drop down to select membrane orthotropic. And here is where I'm going to create a new material. Now, membrane materials are not so straightforward as something like steel A36, A472, for example. This is something that maybe we get from the manufacturer, maybe we do our own testings on these material membranes. So when I go to create a new material, I need to first give it a description. And our material model by default is set to isotropic linear elastic. I actually want to change this to orthotropic elastic 2D. Now up pops my dialog box for my stiffness properties. For this, I'm going to jump back to the PowerPoint here just to show you a quick screenshot here of some calculations. So for my membrane material, I got this from my colleague in Germany, and basically this is the calculations after placing this material membrane into a biaxial testing machine. We apply different forces, we get results based on stresses and strains with those different forces applied. We do our calculations in order to find out what these stiffness parameters are. So that's just a little history about where these particular membrane properties came from. So back in RFEM, we can simply apply those stiffnesses here. For example, it was found that EX is 93 KSI, our EY is 84. Our shear modulus is going to be the same in all three directions at 0.15, and our Poisson's ratio is also important at 0.314. Now I click OK. So we have now defined the specific material that we'd like to use for these surface elements. Now, similar to the cables, we'd like to edit the parameters of the stiffness. Again, these are options that are available, especially this form finding tab when we activate the form finding module. The type we'll use here is constant thickness, and under my next tab, constant thickness, I'm going to set the thickness at 0.04 inches. Then I can click on my stiffness matrix to see those values here. Perhaps I'm interested in those. And under the form finding tab, well, this is the availability to define pre-stresses along the warp and weft directions with our form finding module. So you'll notice that we have two different calculation methods, both the standard and the projection. And this just comes from the general form finding method URS that I mentioned in the PowerPoint. Standard is really used for membranes supported by points or arches or pneumatic structures. Pneumatic just means that they are air-supported structures supported by internal air pressure, which you can see down here is where we can define that internal pressure. Projection is used for conical shapes. So that's actually the type that we have today. But just for example purposes, I want to show you what this form-finding deflected shape looks like by using the standard method to begin with. So you can see why we've chosen the wrong calculation method. So we want to define our forces, you can see down here, are defined according to the warp and weft direction. So this is the local X and Y axis. Now, before I define these, it's very important that we go back to our model, and you'll notice my material is now blue because we specified these specific material properties, and I can right-click and turn on my local axes. Well, if we're going to define these pre-stresses according to the local axes, you'll notice all of my local axes are going in different directions. So this is not good if we're going to apply our pre-stresses globally to all of our surfaces, and yet they're going in different directions. So how can we address this quickly without having to redraw all of our surfaces? Well, if I highlight all my surfaces, I right-click to edit them again. We have a tab called Axes here. Now, Axes allows us to quickly rotate our local axes. And for example, this third option down here, we can point all of our local axes direct to a line. Now, this line can be a fictitious line within the model. Here, for example, we'll choose the origin as the bottom point, which is going right up the center of the structure. And our second point will be at the origin, but at a Z elevation of 35 feet. So now when I click OK and I take a look at my local axes, all of those X local axes are pointing right towards the center of my structure. So this is very important when we're defining our pre-stresses for our surfaces globally here. So now going back to our general tab and our stiffness parameters, under the form finding, here is where we can specify our force in the warp or the x-axis, and weft is the y-axis. Either the, this is also known as the longitudinal transverse directions. So for NX, maybe we'll select 0.55 kips per foot, and we click OK. So now that we've defined these pre-stresses, and I can turn back off my local axes, we'd like to run this form finding calculation. Before we can do so, we do need to support the structure somehow. Otherwise, we'll obviously get some type of instability. So just applying nodal supports at the bottom, I have my typical hinged support here. I can highlight over the bottom. I'll apply just a hinged line support at the top. Nothing special here. So now with this RF form finding, we just click the show results. It's asking me to start the calculation. That's fine. We're applying the URS method. Now remember, we are running the standard procedure now. So in just a few seconds, we'll get our deflected shape based on those pre-stresses. So as we can see for our conical structure, this is not the ideal shape that we would expect. So I think that should immediately flag us that, okay, we probably used the wrong calculation type. So highlighting all of these surfaces again, we can right-click to edit it, go back into our form finding settings, and let's change this to projection. I need to redefine my NX and NY here. And it's also asking me where do I want to apply the preset values from the distance from the center of the structure. We'll set this as 1 foot. I click OK. It's asking me to clear my results. That's fine. Now let's rerun the form finding process. So again, still applying those same pre-stresses, but we're using a different calculation type here to get our deflected shape. And now we can see that this looks much better in what we would expect for our conical type structure. So what does this tell us? Well, in our results, which is now available in our project navigator over here, we obviously can see the global deformations in inches here in our contours, but maybe we're interested in the internal forces of our stresses here. So I take a look at my surfaces, and in particular NX. Now looking at my contours, I see at the bottom I have a stress of 0.566. Well, this matches our pre-stress that we put on the structure for the form finding process, or very close to it. So that's great. That's exactly what we'd expect. Looking at NY, exact same scenario. At the bottom we have 0.53. We applied a 0.55 pre-stress, so that's about what we would expect. Okay, so now that we have done the form finding process, it's time to actually apply some loads to this structure. Now, what we want to do is to maybe create a new load case here, and I can simply do this utilizing my tool up at the top, and I will give the first load case a description of dead load. Now, the action category is important because this tells us how we're going to apply these loads to the ASCE 7 load combinations, and in turn, which load factors should be applicable. So we will keep the dead load for the action category. Self-weight is checked automatically for dead load, so this will account for our self-weight within this particular load case. For all other load cases, we'll leave this as unchecked so we don't account for it twice. We click OK, and now you can see that no loads have been applied to our structure yet, but using the new surface load, we can specify a load direction in the global Z, and I'd like to apply a magnitude here. Now, let's say that this structure is just a basic canopy or something of the sort and really won't see too high of load. So you'll notice I have KSF, kips per square foot right now. Well, I can easily access my units and decimal places, and maybe I want to change my area loads to something more like PSF, for example. I click OK, so now I can apply -1 pound per square foot, a very, very small dead load to the structure. I click OK, and then I can select all of my surfaces. So now you'll see that that dead load was applied to each surface. The hole at the top was taken into account. Everything was done automatically. Now, after dead load, we'd like to apply some wind loads. Now, wind loads for a conical type structure. Well, for this, I'm going to again jump to the PowerPoint because I'd like to reference the European Design Guide for Tensile Surface Structures, and this comes from Appendix A 1.2. As you can see here from these pictures, this is for a conical structure. We have our wind direction here on the left coming straight towards our structure, and we have different zones as we rotate around the structure. And then when we relate these different zones to our tables shown down here at the bottom for a closed-sided structure, we have different wind pressure coefficients depending where we're at on this particular structure. In A, B, and C, you'll notice are all suction type loads, and zone D here is both suction and pressure. So it is a little bit complex in terms of how we want to apply these wind loads to our structure if we're going by this design guide recommendations. I want to show you that it's actually not too complex utilizing some of the features in RFEM to take these different zones into account. So I'm once again going to create a separate load case here. The action category will be wind, and the description here will be wind pressure at column. Now I say at column because a little bit later on I will draw in 3 separate columns around our structure at 120 degrees. So this first wind load case will be that wind direction coming straight towards the column. I click OK. So now that I'm in a new load case from my drop down here, I don't have any loads applicable right now. Putting this into elevation view, my first zone, zone D, from our table that we just saw is this front structure here, but it's actually 45 degrees around this front column. So what I want to do is I want to select this node down here at the bottom, and I'm going to use my rotate copy tool. This time I'm only going to make one copy at 22.5 degrees. Now I want to make sure under my details here to clear out the settings that I used before to create surfaces between my copied nodes. In the same sense, I'm going to do the same thing with my move and copy tool in the negative 22.5 degree direction. So for my wind loads, I previously used this new surface load. New surface load will apply the wind load to the entire surface, which is not what I want in this condition. We have a nice feature here called free loads. So free loads allows us to apply basically any different shape that you can think of, whether that's circles, rectangles, polygons, all to our surfaces. So it doesn't necessarily need to encompass the entire surface. For today, we will use a new free polygon load. Now for this, we just specify our surfaces. We can either select them graphically, or I can type in 1 through 9, or I could leave this as all as well. We're going to apply it in the local Z direction, which is normal to the face of the surface according to the local axes rather than the global. The magnitude here, I determined from that table, will be -9 pounds per square foot. Then I just select graphically my different nodes that I would like to apply this wind load to. I click OK, and now you can see that this wind load pressure is applied to the front of my structure, but not on the entire surface elements here. Now, in the same sense, I'd like to do the same thing at the rear of the structure, but 120 degrees. So I'm going to, again, use this polygon load here in the global Z direction. I'm going to change my magnitude to 8 PSF, and then I click on my different points at the rear of the structure. I click OK, and now we can see that there is a surface load being applied to the rear of the structure. And I just realized that I made a mistake. Looks like, I applied this to surfaces all. It's the same thing. You can leave it as all or type in surfaces 1 through 9, but you can see the display is a little bit different. Just goes back to it's being projected. We can project down through multi-level story buildings as well. But just for display purposes, I'm going to select this as all just so that it's very clear this is a suction pressure at the rear of our structure. Now, in the same sense, I'd like to apply my other zone on the right side of the structure. So we again use a polygon load. We'll type in surfaces 1 through 9 in the local Z direction. My magnitude changes to 12 PSF. This is my highest load around the circumference of the conical structure. Then I select my points. Now, something to note here, I would like to encompass half of this surface. Now, the program has snap settings, again, just like what you would see in AutoCAD. So it recognizes that this is the midpoint of that surface. So instead of creating a new node like I did previously, I can just use this snap point. I click OK, and now you can see we have that suction on the right side. Now, lastly, we have a small zone here to do the exact same process. Surfaces 1 through 9. My magnitude is changing to 5 PSF, and I click on my remaining nodes on the right side of my structure. Okay, so now that we have these suction loads on the right side, we could do the same process for the left side, but I really want to show you those tools that make modeling a little bit more efficient. I mean, we have a symmetrical structure here, so what we can do is just to hold down our control key to highlight these two loads over here on the right and use our mirror tool. Mirror is something that you would find in AutoCAD. It's also available in RFEM where we can create a copy. We can mirror about the global axes and the origin. And I click OK. So now you can see that those loads are now generated on the other side of the structure. So essentially you can see how a very complex load can be quickly drawn within the program, especially for these conical type structures and membranes that would normally be very complex. Now, as I mentioned in the PowerPoint, we want to take into account both pressure and suction from this front-facing wind direction. What I can do is go back to my load cases and combinations, and I can create a copy here. Now, instead of wind pressure, we'll call this one wind suction. I click OK. Now, my loads look exactly the same, but what I want to do is to double-click my load up here at the front. All I need to do is to change this to a magnitude of 7 PSF to account for that suction at the front of the structure instead, so just a different load case. Now we have our wind loads for both pressure and suction. Perhaps I'd like to take into consideration if the wind load shifts at any point along the structure. Well, what I'd like to do again is go back to my load cases, and I'm going to choose my wind pressure at column and create another copy of this. Now this time, instead of at the column, I'll call this one between column. I click OK. So what I'd like to do is to shift all of these loads 60 degrees over from where they're being applied now. For this, I'll utilize my project navigator over on the left. And this has all of my input data just like my graphical view and tables do as well. For example, if I scroll on down to my loads tree, I'll see my 4 different load cases. In LC4, I can expand my free polygonal loads. Well, here I can use my shift key to select all my surfaces, which are highlighted graphically. I'm going to use my rotate tool. This, I'm not going to create any copies, and I am going to rotate it 60 degrees. Again, making sure that everything is clear in my detail settings here. I click OK. So now you can see that everything was just shifted over 60 degrees. Everything was taken into account automatically for our surface load application, and that's all that we need to do. Going back to the load cases, I do the exact same thing, but for wind suction at column, I create a copy, I rename it to between column, click OK. And then here, I just make sure that under my tree settings for loads, I'm under LC5. I select all of my free polygonal loads. I again use my rotate copy tool to make a rotation of 60 degrees. I click OK. And just like that, all 4 of my load cases are complete for my wind loads. Now, lastly, I'm going to create one more load case, and we'll call this one snow load. The action category will be set at snow. I click OK. Now, because I didn't create a copy of any of my previous load cases, I should have no loads in this particular snow load case right now. For this, I am going to go back to our new surface load. I'm going to apply it in the projected Z direction with a magnitude of -8 pounds per square foot. I click OK. I can select all of my surfaces graphically, and here's my projected snow load again with that opening taken into account and all of my surfaces. So that's really all that we have to do in terms of our application for our loading. Taking a look at our load combinations now. So it looks like I forgot after the fact, which is no problem. Going back to my form finding, I can right-click under my general data. I left this as unchecked. Well, I want to check it because I want my load combinations to be created automatically. So you can see that you can always go in afterwards to select that or unselect that. So now going into my load combinations here, I take a look at my actions and I'll see that I have dead load, wind load, snow load. Dead load and snow load, pretty self-explanatory, but wind load, we have 4 different load cases here. So how is the program going to apply these to the ASCE 7 load combinations? Well, right now it's set to alternatively. So alternatively means it will be LC2 or 3 or 4 or 5. We can also choose simultaneously so that all 4 load cases are acting at the same time or differently. Differently means that the program will come up with every different combination with these 4 load cases, such as LC2 plus 3, 2 plus 3 plus 4, 2 plus 5, and so on. So you do have control over those different action categories. Now, combination expressions, automatically the program will create our LRFD load combinations as well as our ASD load combinations. Let's say for membrane design, I'm not interested in applying my LRFD load factors. So what I can do is just to uncheck this for now. I'd rather just generate the ASD load combinations, and I can click on my info button here to see that my load factors are more around 1.0 that I'd like to use for my membrane design. So then under the load combinations, you can see the program automatically generates our ASDE load combinations based on the existing load cases in the program. And lastly, we have our result combination, which is nothing more than an envelope solution for all of our ASD load combinations. Now I can click OK. So let's run one single load combination here just to view how our results will look. So what we're going to do is we're going to utilize the RF form finding deflected shape, which we've already done, and just apply dead load to it. And you can see that solves rather quickly. Taking a look at our results now, it looks the same as what we saw with RF form finding, but now we should obviously see some higher internal forces and such. For our membrane here, we can view our NY forces, our NX forces, for example, in kips per foot as contours. Remember, we have our cable elements down at the bottom, so I can view my members and in particular my internal axial forces for those columns I can view at the bottom of my structure here. So that's what's available in terms of solving for the analysis only within RFEM. Now for membrane design, you could take these internal forces, maybe you have an Excel spreadsheet that you use or you do some hand calcs to do design of the membrane. I want to show you our other add-on module in the program that we can also utilize to do some design checks for our membrane elements. For this, we will launch RF limits. So RF limits is pretty straightforward. This is an add-on module, and when I say add-on module, it's nothing more than just a dialog box that pops up within the program. We don't need to remodel anything. All that we're doing here is specifying some limit parameters so that the program can give us a design check based on internal forces to design capacities. So for this first case, let's rename this case, and we will call it max dead. I click OK. So perhaps for this particular membrane, after our testing, we found out what the max NX and NY internal forces should be, meaning that the material should not exceed these internal forces, otherwise it's going to fail. So we have some specifications for dead load only now. So we're only going to check dead load, and I move on to limit parameters. So my limit description, I can just call this one membrane. Now the object type, I'll select surface here. Now I can either select these graphically, my surfaces back in RFEM, or I can just type in 1 through 9 there because I know I have 9 surfaces. And then here is where I can select my limiting internal forces. For example, I have my NX force here. Well, when I check this checkbox, the program allows me to input in some ranges. Let's say we've determined that the max value for dead load should be nothing more than 0.43 kips per foot, and I want my range to be somewhere in between this range. Now, this is tension only. So if I were to experience any compression forces, well, obviously that membrane is doing nothing within our structure, so we'd certainly want it to flag us. So I'd expect something between 0.43 within the tension range. Same thing for NY. We give it a different capacity of 0.37 kips per foot, and the range of the internal forces must be someplace in between there. So now we're ready to run our calculation. All it's doing, taking the internal forces, bringing it to this add-on module, and comparing to my maximum values that I just input in. So we can immediately see this big red X here. I take a look, it looks like my existing value is 1.396 kips per foot. This is well over the 0.43 that I originally put in. So what can we do to maybe change this? Going back into RFEM, remember that I had defined my pre-stresses, which we can edit them here. Take a look at our form finding tab. These are set at 0.55 kips per foot. Well, maybe I've determined that this is a little too high for my pre-stress forces. So let's change this down to something like 0.14. And we click OK. So now you'll notice it's asking me to clear my results. That's fine. We've lost our form finding shape. That's no problem. We can rerun that either here within RFEM, but if I just go back into RF limits and I click calculate, the program knows that it needs to recalculate the form finding, then apply the dead load combination to come up with those new internal forces. Bringing those internal forces into this add-on module to compare to my limiting values. Now you can see that we're around 0.409. That's within my range, so I get a design ratio of 0.95. So that looks good. Now I can also view the limit checks by surface. So we have our table here of all of our different surfaces. What's nice is that as I'm scrolling down through this table, it is synced up to our graphical view within RFEM, so I can know exactly which surface I'm looking at. So that's good for dead load, but obviously we have a lot more load combinations that we need to take a look at. So let's create a copy of our case here, and this time we'll call it max total. So now for my max total under my general data, I have my controlling internal forces, my capacities for everything that should include dead load and snow load and wind load. So, you know, I've already checked my dead loads. Maybe I'm not concerned with that, but I'll move the rest of my load combinations over here to check for my calculations. Now my limit parameters, again, I made a copy so it remembers all of my information from that last case that we just did, but I probably want to change my maximum values here since we're applying a lot more load. For example, NX max might be something like 1.26 from our testing. And Y max might be something like 0.95 kips per foot, and now I'm ready to rerun that calculation. So I click the calculation button, and because this does take a couple minutes to run, not very long at all, but just for time's sake purposes, I've already ran all of these load combinations in a saved model here. So if we take a look at RF limits, again, this is exactly what I just put in, 1.26.95, and we run our calculation. It brings all of our internal forces, and we get our results here. Well, again, I'm seeing a lot of red here, which probably tells me there's some type of problem going on. But I look at my ratio, and I don't even have a ratio shown. Well, why is that? Looking at the existing forces, I have compression forces, and they're very, very small. So what exactly is going on here? Realistically, from the applied pre-stresses and my form finding, everything should be in tension, at least what I think. So there's something that I'd like to point out that we need to take into consideration. Back under the General Data tab, we have this detail setting here. And you'll notice that default is continuous within surfaces. So what the program does with internal forces, but also with deflections, with stresses, with anything that we can view graphically, it uses a smoothing algorithm to tie all of these values together so that we can make sense of it when we're viewing it in RFEM. Otherwise, it would just be kind of random numbers, not really tied together with these nice contours that we could view. But that's great, you know, that's fine for viewing purposes, but sometimes it's not okay when we're doing design, such as this case. The other option here is constant on elements. So it will not use a smoothing algorithm to tie all of our internal forces for a single surface together, but rather it's going to take internal forces from each FE element into the program. Now, there really isn't a right or a wrong way to do this. It's just purely how you're viewing your results differently within the program. So by choosing constant on elements, we're foregoing that smoothing algorithm to make everything look nice and pretty, but rather just bring in the actual internal forces on each FE element. So now when I click OK, it's asking me to clear my results. I can rerun the calculation, but what's nice is it only takes a split second because the calculation's already been ran. It's just purely how it's bringing in these internal forces into our add-on module. Now you can see that everything looks to be below 1.0 for all of our capacity values. So that's the reason why we were seeing some compression forces. Everything truly is in tension. It's just how we're viewing it within the program. Okay, so we want to create one more copy of this case, and this one we will call max snow, for example. And going back to my general data, I'm going to move all my load combinations over here. Maybe I want to check dead load and snow load only because we have some different capacities for snow loads being applied. My limit parameters, perhaps I'd like to set this, done from my testing, to 1.00 for my NX, and my NY will be 0.72 kips per foot. I can run calculation. Internal forces are already there, so it brings them in here. It looks like we're at 0.96, so we're below that 1.0 ratio, so that all looks okay. So I'd say that our membrane design per ASD load combinations is pretty much done. But remember, we did have those cable elements in there. Well, we can use RF limits to check our cables here as well. So for this, I'm going to create a new case, not a copy, and you'll see why, that we'll call this one cables. Now, I can use my result combination here, which again is nothing more than an envelope solution for all of these load combinations. If I want, I can move all of these load combinations over here in place of this one, or both of them. This is the same thing, it just simplifies our results a bit. Looking at limit parameters, this time we'll call this one cables. The object type here is member. Remember that we have 9 different member elements within the program. Those are our cables down at the bottom. And here we'd like to check our normal forces within those cables. So say we got these values from the manufacturer that produces these cables, and they tell us that you cannot have anything greater than 13.71 kips as an axial tension force within this cable. I'd like my range to be in between. Again, something, it should be in tension. I don't want to see anything in compression. And then I can run my calculation. So keep in mind that these are being designed per ASD, so probably later on we'll come back and check these against our LRFD load combinations, which are more typical for design rather than ASD. But just to double check, for now, if we weren't passing ASD, we certainly won't be passing LRFD, and it looks like we have a ratio of 0.77. So everything looks good so far in terms of our code checks or our design checks for the ASD load combinations. Okay, so now that we've completed the membrane design, let's consider the supporting structure. I mean, the membrane design is great, the cable design is great, but it really, maybe we'd like to incorporate it with the rest of the structure here all within one model. So what I'm going to do is I'm going to get rid of these supports, but before I do so, I want to double click and show you an interesting feature that we have. We can edit this support type or create a new support type, and of course we have our translation and rotation for our restraints. We can also put in some partial fixity here with spring contents, and then we have our nonlinearities. And in my drop down from my nonlinearity, you can see that I have this option called form finding stage only. So what this allows us to do is to apply these support conditions only to the form finding process. Then when we move on to, let's say, our ASCE 7 load combinations, those constraints are no longer taken into account. They don't exist at all. So this is almost like a construction type phase that we can automatically account for within the program. So just a nice powerful feature to do so rather than manually having to do this. For our case today, I'm going to use my project navigator though and open up my nodal supports. I can right click just to completely delete them. I'm going to do the same thing with my line supports, right click, delete. And now putting this into plan view, I'd like to create a ring type member at the bottom of my structure here. Well, I can easily do this by highlighting my node down at the bottom and once again going to my rotate copy tool. Here I'm going to create 3 copies at 120 degrees. And in my detail settings, I'm going to select the option to create a line between the node, but I'm also going to create a member between the node. So when I check this checkbox, I can create a new member type. Now the member type is beam here. This is just any typical type beam or column element within the program. We're not working with cables or anything anymore. So I open up my material or my library for my cross sections, and here is where I can select my circular hollow sections. Again, using the filters on the left, we have the AISC, we have our Canadian sections, as well as many other international standards. For today, we will use an HSS 10 by 0.75, 10.75 by 0.25. Now, the material is steel A36, so I want to create that new material. Utilizing my filters, I see steel A36 up at the top here for my ASTM. I click OK through all of these dialog boxes, and then I see my beam automatically generated around the bottom of the structure. So that was fairly easy. Now, in the same sense, I'd like to create my 3 columns that I mentioned before. So we'll have a column here up at the front and a couple columns here in the back, all 120 degrees apart. So you'll notice I held down my control key to select these 3 nodes, and I'm going to utilize my move copy tool. We will create 1 copy in the negative 15 foot global Z direction. Now, I'm utilizing this feature just to show you some different options within the program. You could easily draw in these columns with a couple clicks too by drawing in a new member. This is just one other way to do it. Under the details settings, we'll utilize the copied lines and members between the nodes and create a new cross section here. So I want to utilize an HSS section, but I'd like to choose a slightly smaller section. We'll choose 8.625 by 0.25. Now steel A36 I've already defined within the model, so now I'll always have this option every time I go to draw a new member. I select steel A36, I click OK. I would like to have a member hinge up at the top, so I'd like the moment to be released at the top of my columns. Well, for this, I can easily create a new member hinge here. I get a nice little picture showing me exactly what my local axes are. The program suggests, well, you probably want to release your Y and Z axes, and that's correct. I'd like to release those for my moment. And you also notice, just like our nodal supports and line supports, we have spring constants here for partial fixity, and we can also get into the nonlinearities such as partial activities, slotted joints, things like that. For us, we're just applying a simple moment release. I click OK through all of my dialog boxes, and my 3 columns are created. Then I can apply nodal supports in a similar fashion like what we did before, just to the bottom of the structure. Now, I want to continue modeling because obviously the center of our structure is not supported, but for this, I'm going to jump to a saved model just for time purposes. You'll see that I have created this column up the center of the structure. I've added some braces to my outer columns here. If I zoom in up to the circular opening, I applied an MC shape, 8 by 20, to that exterior circle. And lastly, just some flat bars to tie it to that center column. These flat bars are just 1 inch by 8 inch bars. So you can model in the rest of your structure here with any type of materials, whether that's aluminum or steel, to account for the supporting structure. So how do we utilize some of our other add-on modules to do a complete design of our membrane structure? Remember that we've already done the membrane design, which you can do so with this structure that I'm showing you right here. But let's take a look at our other add-on module, RF stability. So RF stability is pretty powerful in the sense that we can do a stability analysis to show our different buckling shapes from an applied load. For example, I created this first case here called vertical. I applied my load case dead load. Then when I run my calculation, I get my critical load factors for my structure. So this is based on the buckling behavior of my entire structure with 4 different buckling modes. I can view this graphically, which I think might be a little bit more interesting. So based on the applied dead loads, for example, I have my eigenvectors here, only to a max of 1.0, and they're unitless because it is an eigenvalue analysis. And I can view my different mode shapes. I only solved for 4 mode shapes here, but I can view the different buckling shapes. Now, in the same sense, going back to RF stability, I have created a second case here called wind load, and I imported in my load case number 2, my wind pressure column. I run my calculation, I get my critical load factors for now my first wind load case. Again, I can view all of this graphically to view the different buckling modes. So just quite interesting to show you what the behavior of the structure is under those applied dead loads and wind loads. So why do we do this? Well, back under data, we have another add-on module called RFEM. RFEM allows us to apply imperfections to the structure. Now, imperfections can be related to the AISC, Chapter C, the direct analysis method, where the code tells us that if we want to apply things like notional loads, for example, to account for column out of plumbness or member out of straightness, for example, we can apply imperfections and to manually model these type of imperfections. It's certainly important in Eurocode, as the Eurocode calls for imperfections within all of our load combinations. AISC is not so straightforward with that. It kind of really depends on some different factors, but regardless, it can be applied for all design no matter which standard you're looking at. So when we're looking at RFEM, we can actually import the buckling mode from RF stability. So that was what we were just looking at in our other add-on module. You can see all of my different cases here. For example, my first case, vertical. Now I can export those imperfections that are being generated by RFEM as a load case. So load case number 7, and I've named it vertical. So once I click generate, what exactly does this look like? Well, taking a look at my drop down here, I can take a look at the vertical here, and it looks like it's not showing up quite yet. Let's see. Well, regardless, we can view them graphically, but let me make sure that they are being exported here under our load cases. So like I said, these imperfections are being exported here as load cases such as vertical, wind load 2, 3, and 4. I click OK. Let's take a look at, let's see if any of these other ones are showing up. Yeah, there we go. Okay, so here they all are, and basically this is what it's accounting for, column out of plumbness. We can zoom in here and see this is set at L over 400. So these are just dependent on our normal forces within that column, and then we can account for that column out of plumbness, like I said, or we can account for member out of straightness with these imperfections. So as I mentioned, they're exported in as these load cases, and then under combination expressions, and you'll see here that I activated my LRFD load combinations for design purposes. I unchecked my ASC because now I want to move on to my member design. But keep in mind, you can utilize both LRFD and ASC within one model. I'm just trying to simplify for today's purposes. So under our LRFD load combinations, we can activate this imperfection load cases. Then under here is where we can say, okay, we'll apply this imperfection with this load case and this imperfection with other load cases. So just some parameters here on how to apply those imperfections. Then under load combinations, you can see all of the different imperfections applied with their associated load cases such as wind load. For example, LC2 is the imperfection from wind load 2 applied only to wind suction at column. LC10 is wind load 3 applied only at wind pressure between column. So that's just kind of how we can apply those imperfections to the rest of the structure. Now, lastly, we can run an analysis, a code check here from our analysis according to the AISC module, for example. Same goes with Eurocode or the CSA steel module. Basically, I created two cases here just called beams. I checked all my beams and braces, and I am checking them against my LRFD load combinations. And keep in mind that this module looks very similar to our ASD, or sorry, to our RF limits module. So once you learn one module, the rest of them are pretty intuitive to use, which is nice. And then I also ran a second case to take a look at columns here. We run our calculation based on these LRFD load combinations, and we get our code check directly from the AISC. So it looks like our columns are well below 1, judging by our big green smiley face here, and we also have our beams and braces at 0.73. We can view everything graphically as well to see that everything is below 1.0. So again, this is just to show you guys that you can utilize all of these other add-on modules for a complete structure design. If we want to go back and take a look at our form finding, we can do so here with our membrane. So everything is tied together. Okay, so that really completes the overall structure design. Now the last thing to touch on is the RF cutting patterns. So for this, let's turn this into an elevation view and turn off our results. So as far as cutting patterns, remember we're trying to turn this 3D membrane element into a 2D pattern in order to give to the fabricator, whoever is going to be producing this membrane. And right now, these surfaces are pretty large for our 2D cutting pattern. So, you know, we could take these surfaces and cut them in half, but that would require some remodeling, and it's not very user-friendly. So we have a nice feature in our Project Navigator that we can right-click under lines to create a new line. And again, this is what we saw at the very beginning of the webinar, but instead we're going to choose Cut via a section. So all this is going to do is it's going to apply it to surfaces 1 through 9. We move on to the next tab, and I'm just choosing a couple points here of where to make my section cut. So for example, I can graphically choose up here at my origin. My second point, maybe we'll go with this surface right here. I'd like to choose the cut right down the center, so I'll choose my second point down here. The cut type will be a section, and the definition type will be according to a direction vector. So this direction vector can be something completely arbitrary. For example, I can just put 1 foot here in the global Z direction. I click OK, and now you can see that that line was added to this surface element. This is still a single surface. It's just purely a line that was added. And what I can do is I can highlight this line, and I can use my rotate copy tool, which is the same thing that we've been using, but you can also right click on an element to utilize this tool. Here I'm going to create 8 copies at 40 degrees. Make sure that my settings here are turned off. I click OK. And now the program is going to create a copy across all of my surfaces of just that simple line element. Nothing too complicated here. So now going back to my elevation view, I want to generate my cutting patterns. And for this, I just simply go to Tools, Generate Cutting Patterns from Cells. Now this dialog box is very simple. It's asking me what surfaces to apply it to, 1 through 9. And do I want to ignore any of these lines? Well, no, I don't. I just added these lines to create smaller cutting patterns. So I click OK. And then the program generates these 2D cutting patterns. You can see this little symbol here that I can double click. So when I double click the symbol, it's quickly calculating through to determine the cutting pattern from a single membrane as far as the input data. So this is for pattern number 4, which we can see is highlighted here. And we have some options such as compensation, compensation from boundary line, which as we select these, we get these tabs that are populated up at the top. So taking a look at these tabs in particular, if we look at compensation, remember that these membranes, they are probably going to be stretched when we apply them to our structure. So as far as a 2D pattern, we need to take that compensation into account. Now we can do so whether that's standard in the warp or weft direction. We can even apply it at an angle if we'd like to. So as far as the compensation, we can apply a percentage here, for example, the warp direction or the longitudinal direction of 1%. And we can do so with the weft direction, the transverse direction, at 3%. So this is more of a uniform application to this 2D cutting pattern. Under the next tab, different compensation by lines, well, this allows us to take into account different compensations for each line, boundary line, if we don't want to necessarily do so more in a uniform manner that we did on the last tab. Here we have allowances. Allowances are for welding lines or for border lines. For example, let's say at the top and bottom of the 2D cutting pattern, we'd like to add 8 inches of additional material. Well, we can easily set that by setting this to 0.66 feet. Then down here at the bottom, if we don't want to globally set those again, we can check them on for a different application for each boundary line or welding line. For example, taking a look at line number 72, which by the way, we can always activate our numbering for our lines back in RFEM and have those on in the background as we're looking within this dialog box if we don't know which line number 72 is. But I'd like to activate this because my adjacent membrane may be overlapping this a bit. I want to add in 4 inches to this particular welding line. Now you'll see that the boundary lines are automatically calculated by the program. It's pretty smart with those, but if you're like, oh, that's actually not a boundary line, but I'd rather be a welding line, well, that's where the line type, you can use your drop-down box here to change that. So now that we're done with all of our input, we can click Calculate. Now, what I've done is I have an additional module here that I can launch because what I've done for all of these different 2D patterns is I set each one to have its own border and allowance additional width to it. And then I ran the calculation for all of my different patterns. So now we get a couple different tabs up here, which is our 2D cutting pattern. And once we run the calculation, we get the X and Y coordinates for our 2D pattern here. Now, this is a table, and as I scroll through this table, it is synced up to my little graphical view over here on the right. I can always zoom in, and it's all based around my origin right here at the center about what these X and Y points are. I can also turn on my global mesh here within the cutting pattern. And right now, this is without my allowances, so without that welding and additional allowance at the top and bottom. So I can also toggle that on. You can see here's my 8 inches at the bottom, here's my 4 inches at the side, and my 8 inches at the top. And now my my point coordinates here should reflect these different allowances taken into account, which we zoom in here, we can see this. So here's our option to export directly to Microsoft Excel. I think this is a very powerful feature because obviously Microsoft Excel will have a lot more capabilities in terms of sorting data than what any structural analysis program could do. So we give you that option to do so here. Under statistics, this just gives us our area, our 2D area, our 3D area. Again, you know, we're turning this 3D area into a 2D area based on the minimum energy theory. We also give you the height and width of the 2D cutting pattern with and without allowances. So that's basically all as far as the output for the cutting pattern. Now, let's say we would like to generate this to our printout report, and we'll start with generating a nice picture here of our plan view. Well, for this, I can simply print my graphic, and we'll choose the current view only to use the full page width, full page height. We click OK. So what the program's doing now is it's cycling through to create my printout report, and it takes just a second here because it's collecting all of the input data and all of my results, especially including my cutting patterns, and creating a printout report. So up pops this separate application. And you'll notice that we have our table of contents on the left and we have our actual report printout on the right. And here's that picture that I just generated. So this is my plan view of my different cutting patterns. Maybe I'd like to move this to coincide with my cutting pattern point coordinates down here at the bottom. Well, I can easily do this by dragging and dropping it, and my printout report will automatically update. So I can jump down to that picture again, and if I scroll down, well, here is where my cutting pattern information is. So here's my X and Y coordinates without overlaps, with overlaps. This is for pattern number 1. I have a nice little picture generated here with my node numbers, and I can scroll down to all of my different cutting patterns. So very powerful in how we can present this information in our printout report as well. So one final thing to show you is how to export this information to a DXF file. What we can do here is go to File, Export, and down at the bottom we have this option for formats for cutting patterns according to a DXF. Now we will have an additional tab populated here, and this is where we can export our cutting patterns. And then we just give it a few parameters here, such as the number of patterns per row. Well, I can set this to 3, for example. The distances between patterns can be set at 3 feet. Here is where we can export the 3D shapes or our overall structure. We can also export the cutting patterns FE mesh or uncheck this if we don't want to see it. And lastly, we can export the 2D cutting patterns as 3D face elements. So I click OK. I can save this DXF file, and what the program will do is to cycle through and to export this, and then up will pop a little dialog box telling me that the data export is complete. Data successfully exported to file. So now in AutoCAD, what I can do is just to open that file, which I already have it saved here. This is just the DXF file that I just created. And you'll notice that this is my model that I just created. Here is my 3D element, and here are my different cutting patterns. If I zoom in here, I'll see that each one is labeled according to the different cutting pattern that we had in RFEM. We have our FE mesh that was generated in addition to our tolerances, both for the welding line as well as the top and the bottom offsets here. And of course, within AutoCAD is where we can add dimensions for these cutting patterns, because everything is to scale according to this point coordinates that was created in RFEM. So again, very, very powerful in terms of creating these cutting patterns. Okay, so with that said, jumping back to the PowerPoint, we can sum up today's webinar. I know this was quite a bit of information today, and you can always find more information on our website at dlubal.com. We have many different social media sites. One I really like to point out is our YouTube channel, which has a lot of previously recorded webinars such as this one that you can find. Now, our email for our U.S. and Canadian engineers in attendance today is info-us@dlubal.com. For all of our other international viewers, you can email our German office at info@dlubal.com. The phone number for our Philadelphia office, again for U.S. and Canadian engineers, is 267-702-2815, and for our international attendees, you can call into our German office with any questions or comments at +49 9673 92030. We will have many more upcoming webinars. You can always find these on our website at dlubal.com under Support and Learning Webinars. As many of you know as well, we always send out email reminders to let you know when those are coming up. For those of you in the U.S. and Canada today that would like PDH credit, that's great. I will be happy to issue that. I just please ask that you send the request to info-us@dlubal.com. Again, info-us@dlubal.com. Just let me know who was in attendance for today's webinar, and I will be happy to issue you that certificate. With that said, I want to thank everyone for attending today, and as always, we hope to see you at our next webinar. Thank you.